Hey everyone, and welcome to This Explainer. Today, we're going to transform a simple, messy childhood craft into a totally fascinating deep dive into planetary history. I mean, most of us probably remember making a massive mess on the kitchen table with baking soda and vinegar, right? Well, today, we're taking that basic chemical reaction and using it as a surprisingly powerful scientific model to understand exactly how our Earth, and honestly, even other planets, have changed over millions of years.
So think about it for a quick second. Have you ever actually visited a volcano, or maybe watched incredible footage of an eruption and wondered where on Earth that glowing lava actually comes from, or how it builds the literal, colossal mountains we see today? You know, it's incredibly easy to look at a massive, static mountain and just kind of forget that it was built piece by piece, eruption by eruption, over an unimaginably long period of time. Well, today, we're going to reverse engineer that exact process.
Okay, let's dive into this. We're taking that classic baking soda volcano and giving it a serious, scientific upgrade. We aren't just making fun bubbles today. We're using this Play-Doh and paper cup setup to track actual geological events. By mapping out exactly where the liquid flows during our tabletop eruptions, we can visually capture the history of a volcanic site. We're essentially creating a physical, tangible record of time that we can analyze, just like real scientists do out in the field.
Here is our quick roadmap for today's explainer. We'll start with the classic volcano revamped, move right into erupting and layering lava, introduce the law of superposition, get hands-on with taking core samples, and finally, wrap the whole thing up with real-world geology connections. Starting off with Section 1, the classic volcano revamped.
So the crucial point before we start building is to get our terminology locked in. The molten, liquid rock that lives deep inside the Earth, that's called magma. It only officially becomes lava once it breaches the surface and flows outside. A volcano is simply the vent through which this magma and trapped gas are discharged. And when we talk about a caldera, we're referring to that giant cauldron-shaped depression that forms when the rock near a volcano's summit just collapses after an eruption. We're going to be modeling all of this today.
If you're going to run this 30 to 45-minute activity at home or in a classroom, you really don't need much. You'll need your eruptive fuel, obviously, so about a half cup of baking soda and a cup of vinegar. You're also going to need 3 distinct colors of Play-Doh, which is absolutely vital for tracking different time periods. Finally, just round up some small paper cups to act as your caldera, some poster board for your landscape, pencils for mapping, and this is key, clear 2-inch straws, which we'll use as our high-tech geological coring drills a little later on.
All right, moving to Section 2, erupting and layering lava.
Here's exactly how the process goes. First, you pour about 1/3 of your vinegar into your baking soda-filled cup, your makeshift caldera, and watch that eruption happen. Next, and this is absolutely critical, you take a pencil and trace the exact outline of where the liquid flowed out onto your poster board. Then, you carefully blot up the liquid with a paper towel. Notice I said blot, not wipe. If you wipe it, you're going to totally ruin that boundary you just drew. Finally, take your first color of Play-Doh, flatten it out into a nice thin sheet, and place it precisely inside that boundary. Boom, that represents your very first lava flow.
But here's the thing, a volcano rarely ever erupts just once. So, you're going to repeat this exact same process 2 more times, using a brand new color of Play-Doh for each subsequent eruption. And you have to place the new Play-Doh exactly where the liquid flowed, even if it runs directly on top of your older flows. What you'll quickly notice is that the older layers of Play-Doh actually act as physical barriers. They influence, direct, and divert the path of the newer lava flows. The past literally shapes the future of the landscape. It's so cool to see in action.
Now for Section 3, the law of superposition.
The law of superposition is just a massive foundational principle in geology. It basically states that unless something super extreme like an earthquake faulting has flipped things around, the oldest volcanic layers are always going to be found underneath successive newer flows, meaning the geologically most recent or youngest volcanic layer will always be sitting right there on top. By reading these layers from top to bottom, scientists can literally read the history of a landscape like the pages of a book. The deeper they dig, the further back in time they go.
And this brilliantly illustrates the concept. Think of geological rock layers exactly like a teenager's dirty laundry pile, right? The shirt they threw on the floor last week is buried way down at the very bottom, so that's the oldest layer. But the jeans they just took off yesterday, those are resting right on top, making them the youngest layer. The Earth deposits history in the exact same way, just, with molten rock instead of gym socks.
Okay, on to Section 4, taking core samples. Let's get analytical.
If you're doing this activity in a group, this is the part where teams actually swap their volcano models.
You take those clear 2-inch sections of straw and punch them straight down through the Play-Doh layers to extract a literal core sample. Looking closely at the different colored bands trapped inside that straw, you can answer some pretty critical questions, like which color came first, second, and third. How many layers are stacked in this one specific spot? By taking multiple samples at varying distances from the caldera, you can map out exactly how far each historical eruption spread.
However, here is the huge challenge that real scientists face every single day. Because newer lava might run around older, thicker flows instead of flowing perfectly on top of them, a single core sample might not actually contain all 3 layers. You might punch a straw down and only pull up colors 1 and 3. This perfectly shows why the law of superposition isn't always 100% straightforward out in the field. And it's exactly why real volcanologists have to take many, many core samples across a really wide area just to build an accurate historical map of a site. It's like piecing together a massive puzzle with missing pieces.
Finally, Section 5, Real-World Geology Connections.
Now, what's really interesting about this slide is that your finished Play-Doh volcano probably doesn't look at all like what you expected, right? It isn't this towering, steep-sided peak like Mount St. Helens. Mount St. Helens was formed by very thick, highly explosive lava. Instead, your model is likely wide, flat, and pretty low-sloped. Well, it turns out this perfectly mimics the shield volcanoes you'd find in Hawaii, and remarkably, the colossal volcanoes found all the way on Mars. Those cosmic mountains have low slopes specifically because they're built from layer upon layer of thin, runny lava, literally exactly like our vinegar and baking soda eruptions.
Let's move to and see how this builds into the overarching takeaway of this entire exercise. As our source material beautifully sums it up, by observing the layers of a volcano's flows, we can look back in history to learn about the way that part of Earth has changed over time. Models, even incredibly simple ones made out of childhood craft supplies, are absolutely powerful tools for understanding the massive, ancient natural world around us.
So, I want to leave you with a thought. You are now equipped with the exact same geological principles that top scientists use to decode our planet. So, the very next time you walk outside, whether it's looking at a massive rock cut on the side of a highway, or literally just the soil in your own backyard, how will you use the law of superposition to read the hidden history layered right beneath your feet? Keep questioning, keep exploring, and hey, thanks so much for learning with me today.